Hey everybody, Dr. A here, and in this video we're going to be providing some background information on vectors. Now, this video is really meant to serve a statics course. So statics is typically a sophomore level engineering course that most engineering programs require for graduation. And the prerequisite is Physics 1, right? So what we're going to be talking about in terms of vectors here is really for the purposes of statics, with an understanding that you have already had a course in Physics 1. However, if you are currently in a math course, like a pre-calculus course or a trigonometry course, or even a Physics 1 course, you might also get some good use out of the contents of this video, as vector mechanics and their behaviors is pretty much the same, whether you're in a Physics 1 setting or a math, trigonometry, pre-calculus setting, or a statics setting. However, again, I'm going to be using some vocabulary words that are more specific to statics applications. So let's go ahead and get started. Let's start with the basic definition of a vector. Okay, a vector is a mathematical object that represents a quantity that has a magnitude and direction. Examples of vectors include things like displacement, velocity, acceleration, and force. Vectors are graphically represented by arrows. Okay, so if you want to pause the video and write all this down, that's probably a good idea. Remember, it's really good to write this information down so you learn it best. So, vectors are graphically represented by arrows, so that means we're going to look at things like this, okay? Maybe it's pointing in a different direction like this. Let me draw a little slightly better one for you, okay? They could be vertical. They could be horizontal, okay? Basically just an arrow. They could be pointing in or out of the screen at you, all right? So if you have a vector that's pointing out of the screen at you, like in the third dimension, that might be represented as a dot. If you have a vector pointing in the screen away from you in the third dimension, that could be like an X right there. For most of our applications in statics, though, we're going to be looking at two-dimensional or planar vectors, which would be mostly looking like what I just drew here. Now, when you draw a vector, these vectors, or again represented by arrows, really have two important pieces to them. You have the head of the vector, which is the arrow head there, and then you have the tail of the vector, okay, which is the part that is opposite of the head. All right, so we need to keep that in mind. All right, let's keep rolling. So the length of the arrow itself, or the length of the vector, is the magnitude, okay? The arrow's direction is defined by where it's pointing, typically given as a reference angle. So remember, we said vectors are represented graphically by arrows, and they have two important things, a magnitude and a direction, all right? So if I were to draw a vector here, okay, its physical length right here is its magnitude, mag, okay? Now, its direction could be defined by a reference angle. So if I call this angle theta, maybe referencing from a positive y-axis, that angle theta would define its direction. Another example would be, if I have a vector here, and I have an angle theta measured from a horizontal reference axis, that would still be defining this vector's direction, okay? And then one more time again, the length, the physical length, is the vector's magnitude, all right? Now, let's talk about another vocabulary word that we use when we're dealing with vectors. This other word is called a scalar, okay? What is a scalar? Well, a scalar is a quantity that is characterized by a positive or negative number with no direction, okay? So a scalar is like a constant of some sort, okay? It's just a number. It could be positive or negative. Examples of scalars include mass, length, area, and volume, okay? So a vector's magnitude, which graphically is the length of the arrow itself, is an example of a positive scalar, okay? So we've got two key vocabulary words here. We've got vector, which again is graphically represented by an arrow. It has a magnitude and a direction, okay? And then we have this other vocabulary word called a scalar, which is just a number, okay? It's a positive or negative number with no associated direction, okay? So if we think about scalars, for example, we think, again, mass, length, area, volume. If we think of a vector like displacement, okay? Displacement has units of length. So you might be thinking, wait a second, I thought scalar was a length. Well, length by itself is a scalar, yes. Okay, so length would be units of like inches, feet, miles, meters, etc. All right. A vector, a displacement vector, would have the same units. It would have units of length, inches, miles, etc. Except a displacement vector will also have an associated direction. So when you displace something, you relocate it over a distance in a particular direction. So a displacement would be like 10 miles due east, okay? The 10 miles part is the magnitude, which is an example of a positive scalar, okay? And the due east would be the direction, okay? So that's why we say, for example, displacement is a vector while length is a scalar, okay? What else is similar between scalars and vectors but would be different? How about velocity, okay? Velocity is a vector, okay? The magnitude of a velocity vector is speed, okay? So for example, if you say 60 miles per hour going 20 degrees northeast, okay? That's a vector. That's a velocity vector. You're going 60 miles per hour, and that's the magnitude, and you're going in a particular direction, 20 degrees northeast, okay? But the 60 miles an hour part by itself, that is the scalar part of that vector. That is its magnitude, okay? So when we talk about velocity, velocity is a vector. It's got magnitude and direction, but it's the magnitude of velocity is speed, which is a scalar that does not have the direction associated with it, okay? So this is just things to kind of keep in mind, all right? Now, let's talk about labeling vectors, okay? When we talk about labeling vectors, how do we do that? So typically we label vectors with an arrow symbol above the label or in bold lettering. Okay? So for example, if you have vector A, all right, you can label that as an A with a little vector symbol on top of it. This is like a little vector symbol for labeling purposes. Or, oops, didn't mean to scroll there. Or we label it as a bold letter A, okay? So if you see a letter with a little arrowhead above it, that means vector A. Or if you see a bold letter A, for example, that's also vector A. They mean the same thing, okay? So keep that in mind. Some textbooks in statics and in physics and in math and trigonometry label vectors with an arrow above them. Some label them in a bold letter. So just be aware you could see either one of those. In either case, this is vector A. All right. Now, what about a scalar? Okay, what about scalars? So scalars are typically labeled without any kind of special symbols. There's no arrowhead, and it's not bold. Okay, and so when we think about a magnitude, I'm going to say the magnitude of vector A, which remember is a scalar. Specifically, it's a positive scalar. The magnitude of vector A is labeled as vector A with absolute value bars around it, or A with absolute values of bars around it without the vector symbol, or an A that is italicized. That's a bad looking italics, isn't it? I'll give it an italics look like that. Okay, so how do we label magnitudes, which again, a magnitude is an example of a positive scalar? We either put absolute value bars around vector A with an arrow on it, or you can drop the arrow altogether and just say absolute value of A, or you label A in italics, okay? So again, different physics and statics textbooks and other engineering textbooks might label them one of these three ways. Again, I normally put the absolute value bars around it. I normally use absolute values to really highlight, hey, this is the magnitude of vector A, okay? So just be aware you could see that in different settings. All right, let's talk about scalar multiplication next, okay? When we talk about scalar multiplication, this would be the same thing as scalar division, okay? Because remember, when you divide by a scalar, you're really just multiplying by the reciprocal of that number, that scalar, right? So if a vector A is multiplied by a scalar little c, the product is CA, little c times vector A. And its magnitude is given by absolute value symbols of CA, and is graphically the length of CA. All right, so what do we mean by this? Let's say that we have a vector A like this. Okay, this is vector A. And what is its magnitude? Well, graphically, the length of vector A, that is a really bad dimension line. Let me redraw that for you. Graphically, the length of vector A is its magnitude, so we'll draw that, okay? Now, what if I multiply this vector A by a non-zero constant or scalar c, okay? So if c is bigger than 1.0, then what's that going to do? That's going to stretch my vector, okay? That's going to stretch it out like this, okay? So now I'm going to have CA like this, all right? And what is its magnitude going to be? Magnitude is going to be absolute value CA like this, okay? So we see this kind of stretching effect, all right? What if C is less than 1.0? Well, then it's going to shrink it down, right? You're going to have kind of a shortened CA. And again, this magnitude is still absolute value of C times A, but it's going to be shortened compared to the original vector, all right? What happens if you have a negative value, okay? What happens if C is less than 0, okay? So a negative value. Well, all that's going to do is it's going to flip the direction of your vector. So what you're going to have is your vector pointing in the opposite direction, okay? Pointing in the opposite direction. And again, the length of it is still CA. So that's one thing to keep in mind. For negative scalars, so if you said like -1 times A, for example, it's going to flip the direction, okay? The arrow is going to be pointing opposite of what the original was pointing, okay? So maybe make a note of that here, okay? For negative scalar multiplication, the product points opposite of the original. Okay, so that's a very important key concept here. All right, let's get to the next topic when it comes to vector manipulation. This next topic is going to be called vector addition and subtraction. Okay, vector addition and subtraction. Okay, now here's the thing we got to keep in mind. Remember, vectors have two things. What are they? Magnitude and direction. All right, so because vectors have both a magnitude and a direction, you have to add them in a very particular way. Okay, they don't just add directly like scalars do. You can't just say 2 plus 3 is 5 because you have a direction associated with each of these quantities, each of these vectors. Okay, so let's talk about that. The sum of two vectors, A and B, is sometimes called the resultant, okay, the resultant vector. So we can call that the resultant of A and B, and we write that as R with a little vector symbol, equals A plus B, all with vector symbols, okay? So this is graphically represented by a vector parallelogram, which can also be simplified to something called a vector triangle, okay? So let's talk about what that is, okay? And again, this might be a good point to pause and rewind and write all of this down. Remember, you really should be writing this down if you want to learn this the best. All right, so what is a vector parallelogram? So to form this, what we do is we draw a parallelogram by constructing parallel lines to the two vectors, which are A and B, being added. Okay? The resultant, which remember we're calling R vector, is a vector that extends from the tail intersection of the vectors to the opposite vertex of the parallelogram. So you need to write all that down, all right? So let's say that we have a vector A, and we want to add that to a vector B, okay? And so what we do is we're going to attach their tails together, okay? We're going to attach their tails together. So I'm going to put a little colon here. Attach tails together, all right? And you're going to do this ... without changing their orientations. All right, so do not rotate these vectors. You have to keep them at the same angle orientation that they're in originally, okay? So watch what I'm going to do, okay? I'm going to take this vector A. I'm going to take this vector A here, and I'm going to attach vector B just like this. In fact, let me do it a little better way. Let's just drag this right here. How about that? Okay, same orientation, and then what I'm going to do is I'm going to draw parallel lines to each of these two vectors. So watch this. I'm going to draw a line here in red. This line is parallel to this vector B, okay? Let me redraw that a little bit nicer. But again, I'm drawing a red dash line here that's supposed to be parallel to B. And then I'm going to draw another red dash line here that's supposed to be parallel to A, okay? So I have this red line parallel to A. I have this red line parallel to B, okay? Now, the next part of my sentence is the resultant is a vector that extends from the tail intersection of the two vectors being added to the opposite vertex of the parallelogram. So watch this. I'm going to draw a vector from the intersection of the tails to the opposite vertex. This is the resultant, okay? That is my resultant. And again, I've got parallel lines here to here and parallel lines here and here. And so this collectively is my parallelogram. Now, you know, I kind of extended my parallel lines out. You can trim these down and have this parallelogram here, okay? So that is a parallelogram. Now, we also said which can be simplified to a vector triangle. So here's what's cool about this. Most of the time, even though we have this nice parallelogram here, we only really need to analyze half of it, okay? Because each half of this parallelogram is a mirror image triangle of itself. So really, you only need to really analyze one half of this. So that brings us to our vector triangle. And I'm going to define this. I'm going to say this can be formed in two ways, okay? Both of which lead to analyzing one of the triangles formed by the vector parallelogram, okay? And so what we can do is, like I said before, look at either half of this, all right? So I'm going to copy this over, or just move this down here, okay? And let's see, copy this over here, all right? And what I can do, again, is really just analyze half of this. Okay, I could analyze the top half, like I do here, like I drew here, or the bottom half, like I just drew here. Let me relabel this. Okay, now you might be wondering, how in the world can I do that? What happened to the other vector, right? So if I look at this left option here, it looks like I deleted vector B. Well, here's what's cool about this. Because I drew this as a parallelogram, this length right here, the length of this is what? Vector B, okay? So watch what I can do here. This edge of my parallelogram, I can relabel this as vector B, all right? And same thing over here in this OR statement, I can redraw this edge as vector A, because that was formed in a parallelogram that was parallel to that other vector, okay? So let me write another sentence here, another way we can think about this, because this can be kind of confusing. All right, let me delete this for now. So this can be a little confusing. Let's write this out, okay? Another way we can think about this is the following. We can think of this as translating one of the vectors, we'll say A or B, without changing its orientation, such that its tail meets the head of the other vector. Okay? So watch how another way I can think of this is. If you have that same vector A here, this is the same vector A we've been dealing with, I'm translating that vector B over here to where that parallel line was that was parallel to where B was originally, okay? And so how did I do that? Such that vector B's tail meets the head of vector A, all right? And then guess what? I can extend the resultant from the tail of A to the head of B, okay? So let's write that sentence down. R extends from the tail of the non-translated vector to the head of the translated vector. Okay, so what would the or statement be here? I could say this, or I've got A here. Let me draw it a little bit better for us. I'm sorry, not A. I've got B here. That's where B was. And I translate A somehow. How do I translate A? Like this. Okay. Put my label down here. And then the resultant is from the tail of the non-translated vector to the head of the translated vector. Okay. So in either case, you get R equals A plus B, or you could get R equals B plus A. So A plus B or B plus A, okay? So again, a couple ways you can think about this. You can start from the parallelogram and basically delete one half of the parallelogram, or you can think of it in terms of translating one vector over somehow, okay? But ultimately what you're doing when you're doing the translating is that you're doing it such that when you translate, in this case, vector B, its tail meets the head of A, okay? And in the case where I translated A, the tail of A met the head of B, okay? And then the resultant will extend from the tail of the non-translated vector to the head of the translated vector. So this is kind of confusing, especially if it's your first time learning this. So if I were you, I'd maybe pause the video, rewind it, rewatch it, and really think about it. Write all of this down, okay? Again, I've said it before, this is the best way to learn, okay? So let's get to our next little part of this. Vector subtraction, okay? Vector subtraction. How does that work? Well, guess what subtraction is? Subtraction is just adding a negative quantity, okay? So all we have to do is think of this as add a negative, all right? So how do we negate a vector? Okay, let's say we have vector A, and let's say we have vector B, and let's say we want A minus B, okay? How do I do that? Well, what I do is I multiply B by -1. What does that do to B? Think back to earlier in this video. It reverses B. It makes it point in the opposite direction. So I'm gonna have A looking the same here, but now B looks like this. Okay, this is -B specifically, right? It's pointing in the opposite direction. And so what do I do now? I follow the same rules that I did before. I can draw a parallelogram. I can look at a triangle. So I'm going to make a note here. I'm going to say now follow the same process as addition. Okay, so we go back to what we did all up here. Okay, we can draw a parallelogram, look at half of it, and draw a triangle. Okay? What about vector component resolution? Okay, this is also an important thing we need to know. Okay, we can resolve a vector into two components that lie along different axes. Let's call them U and V, using a vector parallelogram. Okay, so let's say that I have some vector C. Okay, let's call this vector C, and let's say that I've got an axis right here. I'm going to call this the V axis, and let's say that I've got an axis right here. I'm going to call this the U axis. Okay, let me make this V axis a little longer. V axis and U axis. Okay, so what I can do is use this concept of a vector parallelogram and break this vector C down into components that lie along the U axis and the V axis. All right, so it's kind of like going backwards. It's like taking something that's already a resultant and breaking it down into two vectors that pieced it together. Okay, so how would I do this? Well, I would use this concept of a parallelogram. Okay, I'll take this V axis and I'm going to draw a line parallel to the V axis over here at the head of my given vector. Okay, so this axis is parallel to the V axis. Okay, and then I'm going to do something similar with the U axis. Okay, I'm going to draw a line parallel to the U axis popping off the head of my given vector. Okay, something like that. Okay, and so this is going to be parallel to that U axis. And now what I can do is break this vector C down into a vector, let's call it U, and maybe call this one vector V. Okay, and again, using the same concept of forming a parallelogram here, except instead of taking two vectors and combining them to one single resultant. Now I'm starting with one single vector and I'm breaking it down into two components that lie in particular defined directions by, in this case, the UV axes, okay? So that's a useful thing to know how to do, especially in statics, but also probably in physics 1, okay? Now, what happens, we've been talking about two vectors, okay? What happens if we have more than two vectors? Let's write this down, okay? So these techniques can be used for more than two vectors by successively adding, I'm going to say, or subtracting, two at a time. Okay, so for example, if we want a resultant to equal vector A plus vector B plus vector C, we can first perform R1 equals A plus B, then perform vector R equals R1 plus C. So you see we can add them one at a time, all right? However, this does become quite tedious though, okay? So we'll make a note here. This does become quite tedious, okay? What we'll find later in some later videos that when you have multiple vectors, especially more than two, using another technique called rectangular components is going to be more efficient, and we'll do another set of videos on that, okay? I'll also make a note here, most of these techniques require the use of, guess what? Law of sines and cosines, which we've already kind of reviewed in another video, okay? So I hope this kind of rather long video was helpful to you in understanding the basics of vector behavior. We're going to do several examples to help us have a better understanding of this. And again, this is more for the purposes of a statics course, the early material in statics, but this could also be helpful for those of you who are taking a Physics 1 course or maybe like a pre-calculus or trigonometry course as well. So if you found this helpful, please hit like and subscribe and be on the lookout for other videos like this. Thanks for watching.